All right, I'm going to do a short lecture about thermal actuators. You can ask questions anytime. Okay, more questions the better. Now this is kind of a busy first slide. There's a lot of detail in here. But basically what we're going to talk about is how these thermal actuators work, and there's different designs for it. This is one that's a Chevron Design. There's a paper in the unit for this section in the design class that goes into a lot more detail on it. Now you're not responsible for the calculus in here or anything like that. I just wanted to show you where some of these ideas come from and what the math looks like. Okay, so if you just focus on this upper right corner here we have a beam that's a certain length. And then we do something to the beam and make it a little bit bigger. So this is L0 or L sub 0, and this is L. So when we do something to it and it gets longer, it changes by a delta L. So it got bigger. Okay? So what are some things we can do to make a beam longer? Well, here's a hint. You can heat it up, right? If you heat up stuff, most things expand. There's some weird materials that might contract, but for what we do, everything that we add temperature to heats up. So if you have a wire and you pass a current through it, it'll heat up. Okay? If it's a thin wire, it'll heat up even more. We'll talk about that in a minute. All right, so if we want to make something get longer, okay, we'll go ahead and we'll pass some current through it, and then it'll get longer because it heats up. So L, which is this length, what you end up with, and L0, or L0, what you start with, you take the difference between the two, L minus L0, you get a change in the length, delta L. And that's what this is representing here. Okay? Not too difficult. Now if you focus down in the lower left, I wrote a little equation that's delta L is proportional to some constant, alpha, times delta T. So delta L is proportional to alpha delta T. Okay, alpha is a constant that's related to the material you're working with. Okay, it's a material property. So copper will expand at a different rate or a different length for a given temperature change than, say, aluminum. Okay, so you have to have some kind of a constant in here that takes into account the material property. And then you can see if we change the temperature of something by delta T, it's going to get bigger by delta L. Okay, so if you look up the expansion coefficient, that's what this alpha is, you can calculate approximately how much longer something gets based on the change in the temperature. Now if you look at the calculus, right, this is basically L minus L0, which is delta L, is equal to some length that you start with. And now you're going to integrate over the temperature range. So you go from T0 to T, right? Alpha can be a function of T. So maybe copper expands at a certain rate at 100 degrees Celsius and at a different rate when it's at 200 degrees Celsius, which is usually the case. Some complicated function as with temperature. But over small ranges of temperature, you can treat it as a constant. So basically, this is an integral sign, and this is a delta T, and what that comes out to is delta T when you're done. And if alpha is a constant, it just comes out of the integral sign. Okay? So it's proportional to actually there should be an L in here, what you start with times delta T. So I made an error in here. You go ahead and point that out. So it should be alpha L, okay, L0 actually, delta T. Okay, so it's proportional to that. All right, so to recap, Alpha is the expansion coefficient of the material. L0 is what you start with, and delta T is the change in the temperature. And if you think about it, if I have a longer beam and I change the temperature by the same amount, the delta T will be more because there's more stuff expanding. Does that make sense? Okay, so this is some of the math. Now if I arrange these beams like I did here, okay, and these are fixed, these aren't going to move, and this is attached to the beams, this shuttle here, we'll call that a shuttle. Each one of these will expand if I heat them up, okay, and it'll force this shuttle to move up. So there's some resultant force that you can put on this shuttle. Does that make sense? So now I made an actuator. If I heat these legs up, they'll want to get longer, and the way they're arranged in this chevron pattern, that's like a V pattern, chevron pattern, each one of these will get longer, and the resultant will be to push this beam up. Okay, if I heat these up. Okay, and then you'll get some force. And if you put more of these in here, you can produce more force. You're also going to use more power, right? But these thermal actuators for MEMS devices are really strong. They can impart a lot of force. So if you need more force than what you would get from an electrostatic actuator, you probably want to look at using a thermal actuator. Okay? The only downside with using thermal actuators is it uses a lot of power. So if you put this in your cell phone, you're going to eat up your battery if you're going to do a lot of crazy stuff with it. Okay? Any questions on that? None?
When you apply heat to the arms, will the shuttle expand also? Or will it stay?
Not really. That's a good question. So if you apply heat to these parts, the legs, won't this expand as well? To some degree, but you have to remember, I'm going to put the way this works is I'm going to put a plus voltage here and a minus voltage here, or ground it, right? And so what does that mean? That means your current's going to flow through here, primarily. There will be some heat transfer along the shuttle, but not a lot.
And generally, the shuttle is a lot larger than the car, so it won't keep nearly as much of the current flow.
Yeah.
And it has a lot more mass to absorb.
So the shuttle is larger, it has more mass, it doesn't heat up as much, so it won't expand quite as much. There'll be some effect, but it'll be minimal. Okay? Any other questions? Good question. Okay, so to recap, heat is proportional to power. So if I'm going to heat a room, how do I do it? I run electricity through thin wires. If you've ever seen the old heaters, you might even have one at home still. There's like a coil of wire, right? So you have this coil of wire. And then when you turn it on, current flows through it, right? Current flows through this, and it starts getting hot. And you can even see the coils sometimes expand or droop, right, as you heat it up, because they're trying to get longer. And you have it fixed on the sides, so you'll see the coils droop. If you look inside your toaster when you turn it on, they have thin wires in there that heat up, and you can see the wires will move because they're trying to expand. Okay? So back to the point of this thing, heat is proportional to power. And so heat is a change in temperature, will result in a change in temperature, and that's proportional to how much power you put into the system. And in the case of a wire or a thin metal or a thin polycrystalline silicon that conducts, it's proportional to I squared R, where I is the current and R is the resistance, right? That's, what is that called? Ohm's law? Is that right?
No,
V equals IR and power is I squared R, or V times I.
I think I squared R is...
It might be another word, another term, another person who figured that one out. But it's I squared R. And the temperature change is proportional to I squared R over a small range anyway. Okay? Might be nonlinear if you go from 100 degrees to 300 degrees. But that's the basic idea. I'm going to put heat or power into this thing, and the power that I'm using up within the thermal actuator is proportional to the change in the temperature, and the change in the temperature results in lengthening of that beam. Okay? And we can change that delta T by changing R. So if we can make R bigger, make this resistance bigger, we can get a bigger effect on the change in temperature. Does that make sense? Right? Make R bigger, I can get more out of my current. Okay? I'm also going to use more power. So how do we do that? Well, resistance is some constant. This is resistivity. Okay? Times the length of the beam divided by the cross-sectional area. And that works for wires too. Okay? These are all first-order approximations. They're pretty good relationships. But you can see if I make my area, the cross-sectional area of the beam smaller, I can increase the resistance. All right, so let's draw a little picture of that. If we look at the beam, okay, this is L, and this part here is A. So how do I make A bigger? How do I make A bigger?
Increase the width of the...
Increase this width, right? So if I increase this, the area will get bigger. I could change the thickness too. Okay? So if I increase the area, my resistance, what? If the area goes up, my resistance goes down. If I want to get more power out of this thing, or make the temperature move more, then I would want to decrease the area, right? So if I change to blue, if I make my wire thinner, all right, that area gets smaller, doesn't it? So making a smaller area, that means this part here goes down, causes the resistance to go up. Okay, so the thinner the wire, the higher the resistance. The higher the resistance, the more heat I can produce with that wire. Does that make sense? The more heat I produce, the bigger the temperature change. The bigger the temperature change, the longer this L gets, because it wants to expand. Okay, you guys following? Yeah. Okay. Pretty simple, right? But I can do a lot with that. So as a MEMS designer, I can't usually change the thickness because we're designing to poly mumps, and poly mumps at poly 1 is a certain thickness, and at poly 2 is a certain thickness. We can't change the thickness. What can we change? The width. Okay? All right. Okay. So this is another type of thermal actuator. So take a look at this. On the right side, okay, on the right side here, the design's different than the left side, and they're connected right here. So this white line here that I'm following with the laser pointer, this is the current flow. So if I put a plus over here and a minus over here, the current's going to flow through this structure. And it doesn't matter if you go left to right or right to left, same thing's going to happen. So the current coming in and the current going out is the same, right? One of Ohm's laws. It's like water flowing. If you push a certain amount of water in one end of the pipe, you'll get the same amount of water coming out of the other end of the pipe. That's what current is. So I'm going to put I through here. So this will carry a current, this will carry a current, but the right one's going to heat up. The left one's not going to heat up. Why? Because of this. Right? Resistance equals resistivity times L over A. The L's are the same, aren't they?
Yeah.
Doesn't matter. The material is the same. Doesn't matter. The thickness is the same. Right? Doesn't matter. The only thing that changes is down here. Is this width. So if you look at this, area is equal to thickness times width. This one's thin on the right side, and the one on the left side is thicker. Okay? So the resistance on this side is much higher than the resistance on this side. So if I put current through here, which side's going to heat up more? The right one, right? That's why we label it the hot arm and the cold arm. So if the right one heats up more, it's going to want to change in length, isn't it? More than the left side. Is that correct? Yes? Okay. So that's pretty cool, right? This one's going to want to get longer. So what do you think's going to happen if this tries to get longer? What's the end result? It's gonna want to push this way, isn't it? Right? Because this is trying to get longer. This guy is trying to get longer. So if that's going to get longer, this is going to pivot here in the corner. Okay? Because this is thin. It can bend here. And this whole thing is going to want to go to the left. And then you turn off the current, it'll snap back, because this will cool down very, very quickly. And this will snap back. So you can turn the current on and off and have this thing go left and right. Or left and middle, right? So you can push things that way. So that's another design. Okay? So for your assignment, you're going to actually just copy this design for the thermal actuator. Okay, and they have all of the lengths and stuff. You can see they put some dimples in there. Okay. So I want you to copy this this design. You can see here's the, if I zoom in on it, okay. Here's the cold or the hot arm, and here's the cold arm. And notice they make this thin too, so this will heat up. Also makes it more flexible when it's hot. So it's a trick, right? It's a trick they use. All right. So you can see they label these parts. This is a flexure. Anything thin that's flexible, they call a flexure. Okay, here's a mechanical anchor right here. So they anchor it mechanically. You don't want these things to hit each other and short out. Then the current will just go through here. Okay. So let's take a look at what else is on here. Here are some of the design specifications. And you can vary this a little bit if you want. Instead of 2 microns, you can make it 3 so it doesn't break design rules. The idea, though, is, try to make this length the same as what's written here. Okay? And then what you can see here is this will move until it hits this part. So if I zoom in on the end, okay, this will want to move that way. And when it moves that way, it'll eventually make contact with this. See that? And then maybe push this pointer up. Okay? Put that stupid error in there now. I don't know if I can get rid of it, but it doesn't matter. Let's see what else we got in here. Here's some details on the flexure. Okay, you can change some of the minimum dimensions, right? Because polymumps, I think we can, they prefer 3 microns and 4 microns typically on that order. So you can make the widths a little bit thicker, wider. All right? And then on the end here are electrical contacts. So electrical contacts are really important. Notice that they're 100 by 100 microns. Why do we make them so damn big?
Because otherwise they're hard to connect wires to.
Yeah, we're going to connect a big-ass wire to this thing, okay? Now, your hair is 100 microns. So the wires we usually use are like 60 microns in diameter. So we got to put a wire on this thing, right? And we got to hit it mechanically and either wedge bond it or ultrasonically bond it, right? And sometimes they do solder bonds, but that's not typically done anymore because it's really hard to do. So that's why these are at 100 microns, and they have a 15 micron space in between them. Okay, so that's another thing. That's why, we make it so damn big. It looks like it's ridiculously big. So that's always a problem you have with MEMS devices is how do you connect power to them? Okay? And a lot of times when you're making prototypes, you won't actually connect wires, you'll connect probes. And the probes have very sharp tips, they're like needles. And so the probe tip, would actually come here. And I'm drawing it about the size of what a probe tip would be, the tip of the needle. And there'll be one over here. And you come in from different angles so you don't cross the probes. So they look like sewing needles with a little bend on the end. Okay, and then you can see they added this deflection scale, which is kind of neat. Let's get rid of that. Okay, so you could put this on the end, and you can make little marks, and then you know how far you deflected for a certain amount of current. So the way you would adjust the current is you'd adjust the voltage, right? V equals IR. So as you increase voltage, this thing should move more and more up. And then you can calibrate it. If I want to move it 10 microns, I need a certain voltage. If I want to move it 20 microns, I need another voltage. So that's why they put these marks on the end here. And where would those go? They would go over here. See how that lines up? This lines up with this. Okay? So you could put a structure, a deflection scale, right on the end here. So if you're building something new and you're not sure how it's going to work, you have an idea, you did some theory, all of that, and you have a good guess, 3 volts, it should move 2 microns. Well, when you actually make the damn thing, you've got to make sure that your theory is right, and if it's not, then you adjust for it. Okay? And that's what's nice about these type of structures is if you're off a little bit, all you do is add a little more voltage or a little less voltage. Now, if your system can't provide enough voltage, then you have to go back to the drawing board, right? So you're going to just basically copy this design for your next assignment, okay? So does that make sense, how these thermal actuators work? So that's another thing you can think about for the project design, which we'll start talking about next week. What kind of things can we do with all the different things that you've made? I do have one gear assignment and how to make a polar array. So I'll show you guys that because you'll probably need to make some gears. And then there's a library of parts you can use and abuse to make some actuators and things like that. And we can take a look at the different things that you can start thinking about and what other people have done. Any questions?